Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 36 states that in example 6 in our textbook, I'll recommend going through that before going through this question, but it states that it was determined that 17.6 MeV of energy is released when the following fusion reaction occurs, which I've written here. If we ignore relativistic effects, determine the kinetic energies of the neutron and the alpha particle. So one thing we're given is this value for energy. In the example provided previously, we assume, or the scenario where the two hydrogen ions, so say deuterium and tritium dt, are at rest, which means that based on momentum conservation, the change in momentum has to equal 0, such that our final momentum minus our initial momentum have to be 0. Now for our initial momentum, it has to be 0 then, because they're at rest, there's no movement. We would state that our momentum in our right-hand side would be our momentum of our alpha particle, we'll say, plus the momentum of our neutron has to equal 0. So that means that the magnitude of each of these has to be equal, because P alpha would equal negative Pn, but the scenario where the absolute values are equivalent has to be true then. Okay, so we know there's a relationship between kinetic energy and momentum. So of course, kinetic energy, 1/2 mv squared. We could just replace that with p squared over 2m. So now that we have at least an expression for each momentum term, we can relate that to kinetic energy. And just for future use, I'm going to call this equation 1. And so in terms of kinetic energy, the total energy of our system has to equal the kinetic energy of both of these particles. So kinetic energy of the alpha particle and the kinetic energy of our neutron, because again, the first two atoms are stationary. So this is the only energy of our system. And so we can rearrange this expression just to solve for 1. And again, this energy is this term here, the total energy of our system that is released. So we can say that the energy of the neutron, the kinetic energy of the neutron, can just be expressed as the energy released minus kinetic energy of the alpha particle. And again, for future use, I'm going to call this equation 2. And now I'll replace this term with this expression for kinetic energy. So again, kinetic energy of our neutron is the energy released minus the momentum of our alpha particle, squared over 2 times the mass of our alpha particle. But since this has to be true, at least in terms of absolute values, our momentum of alpha has to equal our momentum of our neutron. So I'm going to replace in this equation P alpha with Pn. Pn squared over 2m, 2 mass of the alpha particle. So I'm going to do this just so I can solve for kinetic energy of the neutron, in which if I find it for one, based on this relationship here, I can find it for both of them. So I just chose to do this for neutron. You can do the same thing for the proton. You can flip it around, but this is where we're at so far. So the kinetic energy of our neutron equals the energy released minus, and now I'll replace Pn with this expression 1, solving for what we have for the neutron. So P squared would simply be the kinetic energy of our neutron times 2 times the mass of the neutron, and that is all over 2 times the mass of the alpha particle, right? Our 2's cancel. And we have a couple two expressions now for the mass of the, or for kinetic energy of the neutron, so I'm going to rearrange that to put them both on one side. So So kinetic energy of the neutron plus kinetic energy of our neutron here as well, in brackets, Mn over M alpha equals the energy. I can therefore take one term for kinetic energy of our neutron, be 1 plus this mass ratio, Mn over M alpha equals total energy. And so I can rearrange this to solve for an expression, Ken equals our energy over this 1 plus Mn over M alpha. And so, well, we can find, or we're given actually both of these masses. You can put them in kilograms, or atomic mass units is just as fine because the units cancel out anyway. So plugging in our energy for V in MeV, and plugging in each of our mass values in atomic mass units, we can find that the total kinetic energy of our neutron is simply 14.1 MeV. Again, our numerator was 17.6, and both of the masses are given in the question. And so by equation 2 now, from equation 2, we can substitute our value in for Ke alpha. So Ke alpha, if we arrange equation 2, is simply just the total energy minus Ke of our neutron, kinetic energy of our neutron. We find it to be 17.6 minus 14.1, which we find our kinetic energy to be 3.5 MeV. And there you go. So these are two kinetic energies. We found that based on the kinetic energy and momentum relationship, because we recognize in this scenario that momentum must be conserved, assuming the first two particles are at rest. This relationship holds true where the magnitude of each momentum is equal, and we can rearrange this kinetic energy equation to solve for both kinetic energies. So there you go.